All right, guys, the same reminders as on Tuesday. So the makeup lecture for programming test 1, so please make sure you study that in time. And also assignment number 3 about trees. It's definitely going to be important for your programming test 2. I didn't end up showing you the calendar again, but let's now do it. The connection was a little bit compromised the other day. Let's take a look. So if you look at the semester calendar, so we are now here on the 5th of March. And by 9th March, next Monday, I'll give you the result for your programming test 1, most likely around Sunday evening or maybe early Monday. I'm going to tell you exactly how you can check the score and also get some feedback. And usually there will be a mechanism for you to submit any regrading requests. If you do believe there's maybe some errors, you can feel free to submit it, and then I'll delegate that to the TA to handle, so you don't need to worry about any mistake. But if you do want to speak about the test or course in general, just make use of my office hour. Always happy to talk to you, right? Just notice that the deadline will be 9th of March, right? Hopefully everybody will stay, okay? All right, so that's about the assignment and the makeup lecture. And then, one more thing. So the exam has been confirmed about the dates, but I think most likely it's going to be either in the Sorby or maybe the gym, the exam center. One thing to note, just in case you're wondering, so somehow I agree with other instructors to really have the exam during the same time in the same location. However, our section is only going to write the exam designed by myself. You don't need to worry about studying for other sections of material, right? Don't worry. It just happened that we share the same location and time. Just easier for TA to invigilate. But to really study for the exam, it's just like how you study for the test. Just focus on the materials for this section, right? You don't need to study anything else. Okay. Any questions? All good? Okay. So let's do a very quick recap. And today, it's going to be a little bit mathematical, about binary tree, but I'll try to keep it slow. If you have any questions, do stop me. It's going to be a very foundational lecture because later on when we talk about running time, maybe for different kinds of binary tree, or even binary search tree, you do need a foundational knowledge for today, right? So we'll get there. Let's do a very quick recap as usual. Okay. So on Tuesday, we basically spoke about recursive definition for general tree. Basically, for every node, you can have an arbitrary linear collection of child nodes. So that means you get arbitrary number of subtrees. So this will be something you want to get used to for your assignment number 3 and later assignment number 4. All right, just make sure you get yourself familiar. And then we spoke about the difference between order and also unordered trees. So in general, you have to make a decision at the design level whether you want to treat the order between child nodes to be meaningful or not meaningful. Right? That's something you got to decide. But I think you can think about for our programming test is always going to be a linked list of child nodes, as you will see in the assignment number 3 and 4. Okay. And we just went over the detail about how you can create a tree node in Java. Think about a tree node here. It's very similar to the doubly linked node that we spoke about right before the reading week. So you got previous, you got next, also you got element, right? So here we got elements still, we got parents, which is like a previous, like a predecessor. And also we got an array or linear collection of children. So this will be the lecture version kind of show to you. But for the assignment version and also for the programming test version, you have to get used to a linked list of child nodes, right? Just make sure you practice that version more specifically for the programming test. Okay, I still owe you guys the explanation about this line here. I didn't forget, but I would suggest for today, let me just dive directly into mathematical property. I'll get to this line a little bit later. I'll make sure I cover that, right? Just about, it's more like a how to understand the workaround at a Java level. It's important, but not as urgent. Okay. And we spoke about how you can create tree nodes and also set the references for the child and also parents, right? Just make sure you can follow through the tracing and also the visualization accordingly. And then we talk about how you can compute the depth of a node recursively, right? So you can see this is a recursive method definition and how you can unfold the recursion and to see how to calculate the depth, right? That's something you can also go over as well. I do encourage you to really look at maybe other test cases, choose 1 or 2, also practice yourself. It can be beneficial, okay? And this one here about computing the heights recursively is also very recommended for your exercise. That one requires a little bit more tracing complication because you're going to run a loop for different recursive call. You can see under the loop here, we have to make some recursive call as we go, right? You can see under the loop, for every iteration, we have to recursively call the heights over here. Right? That's something you want to also get used to. And you can find the solution for this exercise. Let me remind you once more. If you go to the lecture site, you can see that under exercises, right here, you can see computing heights recursively in Java. That's exactly that exercise. Do the exercise, or you can just walk over that solution with me, right, in the video. Okay. And then we talk about binary tree. So now we will be shifting our focus a little bit more narrow to be binary tree. And then we'll later on go to binary search tree, balanced binary search tree, and etc. So binary tree, right? In some way, it's a little bit simpler for us to consider. For every internal node, for example, the root, if it has children, it's going to be up to 2 children. It could be no child nodes. It could be 1 child, could be 2 children, but no more, all right? So in this case, let's say if this node here has 2 children, in that case, we call this the left subtree, rooted at the left child. And we call this one here the right subtree, rooted at the right child. Right? You're going to see this kind of recursive construction all the time about left subtree and right subtree. Okay? And then we spoke, this is just about counting things recursively, which we did cover in the general tree example earlier. You can definitely redo it on the binary tree context. And we spoke about this one here. How can you search an element, let's say searching element G inside this particular tree, right? So here there's no trick. So it's not going to be a very efficient algorithm. It's basically like a linear search. You're going to check to see whether or not the G here matches A. If it doesn't, it might be in the left subtree or it might be in the right subtree. So in the worst case, you have to look at both subtrees. Right? So that's something I just want you to make sure you understand recursively how that can be computed. You can look at the solution I proposed to you last time and take a look. Let me give a little bit of a look ahead. This kind of searching is no better than doing a linear search on an array. We can make it better. When we get to the binary search tree, most likely next week, we're going to see if we can somehow organize the contents of the tree in a way so every time when we want to search, we only need to go either to the left or to the right, but not both. That one can actually effectively make our running time rather than linear is going to be log n. That's something we'll see a little bit later. Okay. But for now, just make sure you got this one here. Inefficient, but important to be aware. Okay. All right, so that's about from Tuesday. Any questions? Okay. All right, so let's now get a little bit more mathematical. Let's now understand this sequence here. So back in our asymptotic analysis lecture, we learned about the sum for arithmetic sequence, right? We learned about it, but let's learn the other one. So this one here will be specifically useful for binary tree. Okay, we're going to see that. Okay, let's talk about this one in general. There will be a formula that you have to know how to apply. There are 2 ways you can go for this. Either you just memorize it, but I would suggest, don't just memorize it, because if you somehow got some nerve in the test or exam, if you memorize it the wrong way, you just get the wrong answer. I'm going to show to you. So there's a very intuitive way to really derive the formula within 30 seconds or 1 minute. So if you, just in case you really forget about formula, you can derive it on a sketch paper right away. Okay, that's my intention. But let's take a look, understand what this is. And it's going to be directly relevant to what we're going to talk about for mathematical properties for binary tree. Okay. So geometric sequence right here, as opposed to arithmetic. Let's look at one example, which would be very basically what sequence you will see for the binary tree. Let's now take a look at this. Let's say 1, the sum of a sequence. Let's say 1 plus 2 plus 4 plus 8 plus 16 plus all the way to 10, 24. So this is one example of a geometric sequence. Why? As long as you can identify the 3 components I wrote over there, it's a geometric sequence sum. Okay, let's see. Okay. First of all, there is an initial term. The initial term means the first term right here. So you can think about this is the initial term. Okay, initial term. And let's rewrite it a little bit. You can somehow see the sequence here. 2 to the 1, 2 to the 2, 2 to the power of 3, 2 to the power of 4, and 2 to the power of 10, right? Why don't we rewrite also the first term as 2 to the power of 0? It's going to help, okay? So this one here is 2 to the power of 0, 2 to the power of 1. And the last term here is 2 to the power of 10. Right? Whenever, especially when you're dealing with geometric sequence, it's always nice to really see the exponent pattern. In that way, you can figure out like a common factor, especially how many terms you have. Right? That's important. Right? All right, the second component here, we have something called a common factor. Okay? Meaning that to go from this term to this term here, you got to multiply by some common factor. From 1 to 2, you multiply by 2. Multiply by 2. From 2 to 4, also multiply by 2. And 2 to 8, also multiply by 2. And for the second last term to 1024, it should also be multiplied by 2. So you will know that this will be just 512, right? So you can see the pattern there. Okay, just about common factor, okay? Like a common difference in arithmetic sequence. And the final bit is the tricky one, okay? Number of terms over here, which will be k. In this case, how many terms do we have in the sequence? The way to see it is look at the exponent. The first term got exponent 0. The last term got exponent 10. So go from 0 to 10. It's as if you got an array of indices 0 all the way to 10. Then what's the length of the array? 11. Agree? Okay? Okay. I hope it's still gentle to you, right? Just make sure you follow every step. Okay. So in this case, k will be basically from 0 to 10. Right? Remember, we talk about interval size, right? So in this case, it would just be 11, right? 11 terms. And now we want to work out a formula, say in general. You may have only k terms, and k can be 10, can be 100, can be 1,000. How do you figure out the formula? Okay? Let's now talk about it. Okay? Let's now derive the formula. Right? Of course, when I'm illustrating to you, it's going to take longer than 1 minute. But when you really practice this, hopefully you'll be quick. So just in case you forget about the exact formula. So we talk about geometric sequence sum, capital S, and we got k terms. Okay? That's how we start with. And then it's going to be the initial term, I, plus I multiply the common factor. That gives you the second term. Plus I multiply, basically this one here multiplied by another r, which will be r to the power of 2. Agree? I multiply r to the power of 3. One more. I multiply r to the power of 3, and etc. And then we're going to go all the way to the very last term. K to the, r to the power of something. All right? Now it is important to see. In total, right here, we have k terms. What should this be? Exponent. Knowing that we got k terms in total, and we have the initial term, we have the pattern, what should be the last term here? What should I fill out in that box? Before anybody try, again, it's always important or useful to also try to rewrite maybe the first term here a little bit to help you see even more clearly the pattern. This one here will be as if I multiply by 1, which will be r to the power of 0. Right? So now you can basically see exponent 0, exponent 1. Of course, I can put 1 here too. Right? Exponent 0, exponent 1, exponent 2, and 3, all the way to something, which will make the whole sequence containing k terms. Right? So now, once you fill it out, yeah? K minus 1? Yeah, absolutely. Okay, hopefully that's straightforward for everybody. Thank you. Absolutely. So now I'm just going to put K minus 1, okay? K minus 1. All right, very good. Okay, so now we want to figure out a formula for this SK. Here's the trick. That's the only small step you have to remember. Okay, that's also for me. I also remember this small step. This one here is SK. Let me multiply the common factor to this SK and see what happened. Okay, so what I will do is I'm going to have another sequence, which will be R multiply SK, which means multiply the first term by R, multiply the second term by R, and etc. All right? If I multiply the first term by R, it's going to be I times R, right? And let me align that right here. And if I multiply the second term by R, it's going to be I multiply R to the power of 2 plus I multiply R to the power of 2. And then multiply this one here by R plus I multiply R to the power of 3. Okay, let me make it more explicit for you. Okay, think about what we have been doing is this one here multiplied by R. We got this. And this one here, second term, multiplied by R, we got this. Okay, one more. And this one here, multiplied by R, we got this. Right? And so on. Okay. And let's keep going and to see how this sequence should end. Plus all the way to over here. Okay? Imagine that before this term, it should be I multiply R to K to the minus 2, right? If you multiply this one here by R, it's going to be exactly K minus 2 plus 1 will be K minus 1, right? I times R to K minus 1, okay? And one final term. What if I try to multiply this term here also by R? K minus 1 plus 1, K. Plus I times R, K right here. Okay, let me just annotate this one as well. So think about this one here, multiplied by R will give you this second last term. Finally, if I do multiply this one here by R, I got this. So the number of terms I got in the second sequence remain the same. It's just that somehow you can think about being shifted, right? So now, here's the thing. Would you agree? Here, this part here is completely identical, right? This one, that's why I kind of aligned that way. If I try to subtract this term from over here, I can cancel everything in the middle out. And then got only this one minus this, right? I can do that. All right, let's try that, okay? So what I will do is, let's now try to do R times SK minus SK, right? That way I can cancel out the middle part, which will be equal to this minus that. I times R to the K minus I. And do a little bit of factoring. It will be I times R to the K minus 1. Okay. Let's see what we got. Oh, also for this one here, we know that this will be R minus 1 multiply SK. Just factor SK out. Right? So now let's focus on two terms. We got this one here. Also, this one here. Now we can solve sk just by rearranging the term. So this one tells us sk will just be equal to this whole thing divided by this. I times r to the k minus 1 divided by r minus 1. All right, so that's the general formula. Okay. In this course, knowing this formula will be very useful, but let's now talk about even more relevant to what we're going to talk about today. Right? Since we talk about binary tree, if you think about it, binary tree, let me sketch a little bit, and I'll do the more detailed illustration in the next page. 1 here means I got the root. 2 here means maximum I can get exactly 2 children in the next level. 4 here means I can get to the next level with exactly maximum number of children for each node. So I got 1, and then 2, and then 4, right? So the common factor for binary tree in this case is just 2 because it's binary, right? Let's write something down here, and then we'll talk something even deeper, okay? For binary tree, the initial term is simply just 1, and that one denotes the root of the binary tree. And the common factor, r, is equal to 2, right? Because every node maximum can have 2 child nodes. That's why it's 2, all right? Let's now apply I being equal to 1 and r being equal to 2 into the formula, and we can simplify that even further, okay? Let's try that. So now if I simply take this sk, will be, first of all, I will be just 1. Multiply, r here is simply 2. 2 to the k minus 1 divided by, again, r is 2. 2 minus 1, right? So what we got is 2 minus 1 will be 1, so we can cancel, or we can get rid of the denominator. So that'll be 2 to the k minus 1, all right? So this will be the final thing if you want to memorize something. You guys are still young, so I'm pretty sure you will stay long, okay? This one, 2 to the k minus 1. So the k here is really about how many levels of the nodes you're trying to sum up, okay? I'll make it a little bit more elaborate in the next page. But I'll make a note for you. But when you study for this part of the lecture, you can see that right away. Okay. So the k here, very common, is going to be the height of the tree plus 1. Why? I'll explain that a little bit later. Right? For now, I just want to give you the facts. Okay. Usually will be h plus 1. H will be the height, but plus 1 for some other reason. Okay. Guys, any question so far? Good? All right, I would suggest for this formula here, think about what you really want to get from here, but I would suggest for the complete learning, try to know how to derive the formula, and also try to look at the final bit, 2 to the k minus 1. And the k here is about how many levels of nodes you want to sum up for the binary tree. All right. And let's now move on to derive something together. All right. And what I'm going to talk about right now will be slide number 26. Right. You will see some nice diagram here on the slide, but let's build it up from scratch. Right. I think it's more beneficial for you. Okay. Let's look at that. Okay. Binary tree. What I will do, let's now first of all remind ourselves about the formula, which we just derived. In general, sk would just be initial term multiply common factor to the power of k minus 1 divided by r minus 1. And when we talk about binary tree, it's going to be 2 to the k minus 1. All right? And the k here, as we'll see, is going to be very often the heights of the tree plus 1. Okay, we'll see. I want to remind you first. Okay, let's now try to build it up from scratch. Okay, I'm going to build more like a table to really talk about different scenario, going from the smallest possible to the largest possible. Okay, So let me now put here. Okay. So I will start with the binary tree structure. We're going to visualize it. Okay. This will be one column. And then we talk about the level. Level something. All right. And then quick reminder. Whenever we talk about level, we really talk about the depth of the node, right? You'll be level 0, all the nodes with depth 0, which will be the root, and so on, right? You will see that. So this will be the depth of the nodes in that particular level. And then the next column is going to be the maximum number of nodes at that particular level. I'll write it down, and then we'll see what exactly that means. Maximum number of nodes at that particular level. All right. So let's examine the binary tree from the root, which will be level 0. All right. Let's start from the root, which I will, you know what? Let me just get rid of that just for now. Okay. So we can make more space for ourselves. Okay. Okay, I'll put it here. Okay. So let's start with the single node at the top, which will be the root. And remember, the definition for depth is about the number of edges to the root. So what's the depth for the root itself? 0 by definition. Okay. So level will be 0. What's the maximum number of nodes we can have at level 0? Just 1, just the root. Right? That was easy. And let's rewrite this one here right away. Right? Given that we know for binary tree, the R, the common factor, is 2. Right? So this will be 2 to the power of 0. It's going to help us identify the pattern. Okay? But usually if you just write 1 to begin with, but later on when you got everything there, you might still decide to rewrite it to the 2 to the power of 0 at some point. Right? Let's do a few more levels. What will be the next level? Next level, you got to think about basically from the root over here, I want to reach out to the next level. How many nodes maximum can I have? 2. Cannot be 3 because it's a binary tree. Cannot be 0, cannot be 1 because it's not maximum. Got to be the maximum. Okay. So what we have is branch out exactly 2 nodes. So we got 1 here and 1 here, left and right. You can think about that's the left and that's the right. Left child and right child. Okay. And this will be level 1 because for this node, the depth is just 1 link to the root. For this node as well, just 1 link to the root, the parent link. Okay. And maximum of nodes of depth 1, 2, right? Because you got exactly these 2. You cannot get more. So that will be 2, which is 2 to the power of 1. One more, and then we'll try to generalize the pattern. So typically, when you want to kind of derive some formula or general property, you may just want to try some small examples. I would say usually a small example of size 0, 1, and 2, or even 3. That's typically sufficient for you to see the overall pattern, right? Just true for math in general. And how do we reach out to the next level in the maximum sense? That means every node in level 1, I should have the maximum number of children. In that way, I got 4, right? So that one there. That means for this node here, from level 1, I got both left and right. 1 here and 1 here. Also, for the other node at level 1, I also got 2 nodes maximum. 1 here and 1 here. And of course, so far, this is level 0, this is level 1, and this is level 2. And we got exactly 1, 2, 3, 4. 4 nodes, which is 2 to the power of 2. And you can already kind of see the pattern here. You can see exponent will be 0, 1, and 2, all the way to something. It cannot be infinite because tree is a finite data structure as far as we are concerned, because a computer is got to be finite, right? Constrained by the memory, which is not infinite. And now we want to see what should be the bound for this, right? So now we have to bring in, whenever you want to think about what's the bound for the tree, think about its height. How tall can a tree be, right? And what's the height's definition? It's going to be the maximum depth for the descendant nodes, right? So you can think about if we keep expanding maybe the link downwards, there's got to be at some point we can reach the bottom nodes, like an external node at the bottom level, right? And this will be constrained by the heights of the tree, right? Let's now write it down and I'll explain to you, okay? So we can keep expanding until we get to the bottom level right here. Oh, actually, let me write maybe a few more over here. And then we can expand just one more over here. Okay, we can keep expanding. Let's say the deepest node is simply just on the left branch, let's say, you know. So let's say this is the deepest node with the maximum depth, basically, all right? And by definition, the number of edges for this deepest node go all the way to the root will be the heights, all right? So now, let's now go accordingly. Think about from here to over here. We'd say it's the heights of the tree. Okay, let's write a little bit more description here. So that will be the number of edges from the deepest node to the root. If I count 1, 2, 3, all the way to over here, how many edges do I have? So that'll be the heights for the tree. All right? So that's all good? Okay. So that's just about how tall the tree is. But now we are talking about for every level onwards, including the last level, we want to get a maximum number of nodes. So now we're going to see the pattern. All right. So this one here, let's say here. Okay. So let me try to get a tree a little bit more in shape so you can see that more clearly. Think about this is going to be the overall tree that we are considering, okay, like that. All right, that's a tree. And then the bottom level here is with the depth h, which means that one there is level h. And then we have level h right here. Now the question is, what's the maximum number of nodes at this bottom level, according to the pattern? Anybody? 2 to the power h, exactly right. It makes sense, right? Because you can see for level 0, 2 to the 0. Level 1, 2 to the 1. Level 2, 2 to the 2. Level h, 2 to the h. Right? Okay, good. All right, so that'll be 2 to the h. Right, just go back, go upward, just one level, right? Think about the previous level. Let me draw green. The previous level, which will be here, that one should be of depth h minus 1, right? That one there should be h minus 1. Level h minus 1. And then 2 to the h minus 1. And then so on. That's the pattern. So this kind of derivation here is so important. Just make sure you practice that and make sure you're convinced, right? Of course, the critical point is we know how to bound the tree by the actual height of the tree, right? Once we know about h, we can know where to go, where to end in the rows. And let's now do the final bits. Okay? So we are going to ask the following question right here. Okay, I'll put it here. Following question. Okay. What is the maximum number of nodes in a binary tree with height h? We kind of know for each level what's the maximum number of nodes in that particular level. Now we want to sum them up. Right? It's a geometrical sequence sum. Okay? So what we do is we're going to sum up this plus this plus this plus this plus this all the way. Right? So we're going to say 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus all the way to 2 to the h minus 1 plus 2 to the h. All right? So what should that be? Of course, you got two ways to really proceed. Either you can simply just go to back to the original formula. Well, that one there you got to apply I being just 1 and also R being 2 and then figure out how many terms we have and the K. You can get one answer. Or you can just go directly to here. That's already a simplification we had, right? Let's apply this. 2 to the K minus 1, okay? 2 to the K minus 1. However, the K here, what should that be? K simply means how many levels or how many turns do we have in that sequence. Now, how many? What should I put? You cannot just put K. K is not even, does not even exist in this context, right? How many turns do we have? From exponent 0 all the way to h? Yeah, h plus 1, exactly, right? That's why I mentioned you'll be h plus 1 here, and also h plus 1 here, right? That's kind of mentioned to you beforehand, okay? All right, so that one there is going to be h plus 1. All right, so given we got height h. Okay, let me recap, and then we can take an earlier break today, and then we'll move on, okay? So geometrical sequence, make sure you know how the formula works, and you'll be even better if you know how to derive it. In the case of the binary tree, this will be the simplified form, but you ought to know how many levels of the node you're trying to sum up, right, the K. And then this page here, we started with the root and try to branch out as much as we can for each level. But there's got to be some limits about where this tree will actually go. So we just use the height of the tree, just have use some value h. H simply means for deepest node in the tree, how many links it will take for you to go all the way to the root. So that's h. Right? So once you get this kind of bound and then try to enumerate about all the levels, you will get this sequence over here. And then you get a sum. Right? So that's the rough picture. You want to make sure you know how to derive. And after the break, we're going to see how we can kind of put a lower bound and upper bound on different measures of the binary tree. And this formula here will still be useful. Right? We'll get there. Right? Any questions? Okay. Okay. Why don't we take a slightly earlier break, about 1 minute from halfway. But let's take a break. Okay. So before the break, we have done with the derivation of this diagram here. We can also take a look at the slides and geometric sequence, right? Oh, we also did it. Okay. And before we get to more, okay, let me see this. Okay, we got, yeah, that's also the same as what we did before the break. Okay. Right. So before we did more mathematical properties of the binary tree, we'll do that. But let's now use this also as like a case study, you know, for how we can also make use of the formula, do some interesting calculation. Given a binary tree, we have two more like a special cases for binary tree. So one is called complete binary tree. Another slide talks about full binary tree, right? Complete binary tree, we'll get there in a moment. And also another term is called full binary tree. We're going to see these two together, right, side by side. Okay. For complete binary tree, the definition is a little bit tricky, right? Because there's multiple parts for the definition that must be true simultaneously in order to be a complete binary tree. But we're going to look at that by using an example to show to you. Just before I get to the definition, let's now look at one example here, right? For now, you can just ignore this part here. That's going to be the full binary tree. Don't worry about that part just yet, right? Let's focus on just this part, right? Let's look at this binary tree here, okay? The height for the tree is 3. First of all, you want to ask yourself why. The deepest node, for example, is H or I or J, right? Deepest node. What's the height? What's the depth? 1, 2, and 3 to the root. That's why the height is 3. Okay? Whenever you're given a complete binary tree, you have to think about 3 parts of the tree. All the 3, each part ought to satisfy certain criterion. If they all of them satisfy, it's a complete binary tree. Okay? So let's now, first of all, divide the binary tree into different levels. So think about this one here. Just continue the root. The depth is 0. And next level, the depth is 1. Next level, the depth is 2. And of course, this one here, the depth is 3. All right? Makes sense. And in this particular case, in this particular tree, because H is 3, so you can think about this depth over here is exactly H. So that's the bottom level. The bottom level is the depth is simply the H by definition. The previous level over here, you can think about it as the second last level, which will be H minus 1. All right? And even above, this one here, the third last level, which will be H minus 2. So you can think about this part over here is really from level 0 all the way to and including H minus 2 levels. That's the first part we have to worry about for the definition. And then the second part is about the second last level, which is with the depth H minus 1. The third part is the bottom level, which is of H, depth. Right? So these are the 3 parts you will see in the definition. We're going to verify all the 3 criteria using this example here. But you can draw more complete binary tree after classes just to convince yourself. All right. Let me just also help you a little bit to really see this. Okay. The first part that we're going to see will be this part here. From level 0 all the way to H minus 2. Okay. And then the second part is actually going to be just the level H minus 1. And the last part will be just the bottom level. So these are the 3 parts, right? Let's now look at the definition. Okay. Okay, if I can, maybe I can just get rid of this. Okay, I think it's a bit better. Okay. All right, part 1 of the definition. The nodes with the depth less than or equal to H minus 2 has exactly the maximum number of children. How do we double check this? So that means the nodes with depth 0 and depth 1, which will be exactly H minus 2. All these nodes have exactly 2 children. Why? A here, 2 children. B here, also 2 children. C here, also 2 children. So this one somehow ensures you will get a maximum number of children all the way down to H minus 1 level. That's something you can think about why. All right? Okay, that's criteria number 1. All right? Criteria number 2. At specifically the level H minus 1, you may have 0, 1, or 2 children. Sounds very flexible. Basically, you can have no children, you can have 1, you can have 2. All right, so now let's double check. So now at this particular H minus 1 level here, you can see this node here has exactly 2 children. Good. This one here has one child. And these 2 have no children, 0, 1, or 2. So that one also satisfied. All right, so far we talked about 2 criteria. And the third criteria goes like this. At the bottom level, it should be filled out from left to right. This is important, all right? So if you look at that here, so at the bottom level here, you can think about these nodes, right? So let me just clarify these, right? Because there are different ways for you to refer to these nodes at the bottom level. Think about right here. So there are at least two ways for you to refer to them. So you can think about one way would be, you can think about they're simply the nodes with the depth simply equal to h. That's one way. Or you can think about they are the children of the nodes with depth h minus 1. At the same time, they are also the children of nodes at level h minus 1, right? They are really referring to the same set of nodes, right? And they should be from left to right. You can see left child, right child. And this one here, let me clarify, it's not exactly clear in the diagram. This link over here, I really meant to say it's left, all right? Left, okay? Hypothetically, if I give you something like this, right, I can clarify right away, okay? And then we'll go back to the, that page, okay? I'll draw that. What would not be a complete binary tree? One example. Let's say, for example, let's say this is my complete binary tree, which I claim. And this part here would just be h, right? Let's say for this part here, I satisfy criteria number 1 and 2. So over here, it's completely okay, right? It's completely filled out, basically, okay? Completely. But at the bottom level, the children are not exactly filled out from left to right. For example, let's say this node over here, I have the left child. And then I don't have a right child for that node. The next node over here, I have another left child over here. So this is not a complete binary tree, because if you look at over here, it's not exactly filled out from left to right because it kind of jump. There's no right child over here. It's got to be exactly from left to right based on the nodes in the level h minus 1. Okay? I'll write it down. Not complete binary tree because let's say node number 1 and node number 2. Okay? Node number 1 has node right child, but node 2 has a child. So think about visually, it should be exactly from left to right, right? Okay? You can create other examples. That's not really a complete binary tree. Okay? So the third criterion just requires a little bit of visualization to see how you can fill it out from left to right. You cannot jump any nodes. Are we okay with this? Okay. Okay, let's go back here. Okay. So now that we can understand about the complete binary tree, so we do have some flexibility here. Okay. It's really up at the bottom level here. Okay. Let's now consider this a little bit more general. And then we can figure out what will be the minimum number of nodes you should have for a complete binary tree, and what's the maximum. So there should be a range of nodes you can have, right? Let's think about we got height h, right, to start with, okay? And this will be the part of the tree over here. So we talk about from level 0 all the way to level h minus 2. If you recall criterion number 1, every node over here should have exactly 2 children, including all the nodes at this level here, h minus 2, they should also have exactly 2 children, right? Exactly like that, right? So you can think about right here is about criterion number 2, okay? Okay, let me just annotate a little bit to help you understand, right? And then we can count. So think about this is level h minus 1, okay? And then we also have the bottom level over here. So this will be h. All right? If you think about the minimum and maximum, right? They are going to share this part of the tree being completely full, which means every level from level 0 all the way up to and including level h minus 1, we got exactly the maximum, which we know how to visualize, right, in the previous page. But now here in the bottom level, we have some flexibility as long as it's from left to right. What will be the minimum, what will be the maximum, right? Let's sort this out individually, and then we'll write it down mathematically. Given that this part here has to be completely filled out, what will be the minimum number of nodes I can have right here in the bottom level? Minimum. 1. Question here for you. I agree. Correct answer should be 1. That means I got exactly just 1 node at level h. I agree. However, let me ask you, why can it not be 0? Which means I have no node at this level here. What's wrong? Not exactly. Not exactly. It's something a little bit even more fundamental. Yeah, go ahead. Very good. That's exactly right. Guys, what your fellow student said is spot on. Okay, let me say it again. The reason that the minimum case is not going to be when you have no node in this bottom level. Because if you have no node in this level here, your initial assumption is h is wrong. The height should be h minus 1 rather than h. Okay, very good. Okay, so the minimum will be basically when you got exactly 1 node right here. So that'll be the minimum case, just plus 1. How about maximum? Plus how many? How many nodes can you have maximum at level h? 2 to the h, right? That's something we said earlier, right? But it's okay. Just get yourself familiar with these, before next Tuesday. All right? So we got minimum, we got maximum. Okay, let's now try to make the calculation systematic. Let's say this part here, just this part, is going to be the same between the minimum and maximum. I'm going to calculate to see how many nodes I have maximum from level 0 all the way to level h minus 1, right? Let's now write it down. That one there is going to be 2 to the 0, 2 to the 1, plus all the way to 2 to the h minus 1. Right? And then in the minimum case, I just got to say plus 1. Just that 1 node. And for maximum, this part here will also be the same. 2 to the 1 plus all the way to 2 to the h minus 1, and plus when the maximum, when the bottom level is completely filled out, which will be 2 to the h. So this part over here is common. Okay, I'll put a star here. What should that part be? All right, now we're going to apply our formula. It's going to be 2 to the power of k and then minus 1. And the k here is going to be how many turns we have right here. How many turns do we have just for this part? We go from 0 all the way to h minus 1. H turns, right? All right. Again, the way I see it, 0 all the way to h minus 1. I got exactly h terms. All right. So this part here will be 2 to the h minus 1. That's good. And then we're going to see, how about plus 1 here and plus 2 to the h? Let's now make it final. Okay. So for the minimum case over here is going to be 2 to the h minus 1, which is here, and then plus 1, which will be 2 to the h. All right, so that's a minimum case. All right. And for maximum, we basically just add one more term, right? For the maximum, right here, it is going to be 2 to the h minus 1, which is the common part, plus 2 to the h. right? You can do the simplification, right? You can think about in here, 2 to the h multiplied by 2, which will be 2 to the h plus 1, and then minus 1, right? All right, so that will be the maximum case. Even though you're still not exactly proficient with the formula, but you can see the big picture. We have to kind of manipulate this sum in different scenarios. Just make sure you can redo this kind of exercises, without any doubts over the weekend when you kind of catch up with the material, okay? All right, so that's about complete binary tree. Full binary tree is much simpler, okay? Definition is simple. We're simply saying for every level, you got exactly the maximum number of nodes. All right, so now in this case, I can just make it, let me just write it down, and then I'll do some comparison for you, okay? So think about, in this case, we are saying at the bottom level here, we have no choice. You don't have any minimum or maximum. They're really the same. You got to be the maximum number of nodes. So it's going to be all the way filled out, which will be 2 to the h, right? I mean just the bottom level. And accordingly, for minimum and maximum, what we have is 2 to the 0 plus 2 to the 1 plus all the way to 2 to the h at the bottom level as well. Okay? This will just correspond to the maximum case for complete binary tree. So think about a full binary tree is just a special case for the complete binary tree when you reach the maximum. That's a way to think about it. I'll draw it out in a moment. All right, so this one here would just be 2 to the h plus 1 minus 1. Because you got exactly 0 to h, you got h plus 1 term, right? And then minus 1, okay, the formula. Any questions about this? All right, let me do one more comparison, and then we'll move on to a bit more properties. So minimum, maximum will be the same right here, okay? Let's now do one more comparison. Okay, put it side by side. So you got complete binary tree right here versus you also got full binary tree. Okay. And let's say given the same heights, h, right here, okay? And then let's draw the general tree shape out, and then we'll see how to compare. Okay, this is one right here, and this is another one. Okay, so let's now talk about from level 0 all the way to level h minus 1, okay? Think about right here, and also right here, okay? Think about this part here should be completely filled out. So this will be h minus 1, right? H minus 1. So that part there should be completely filled out. And in the case of the complete binary tree, this bottom level, it could be number of nodes at level h. Could be between 1 and 2 to the h. There's a wide range, right? On the other hand, this part over here, you have no choice. You got to be completely filled out. 2 to the h. All right, so that's the main distinction between the two, right? You ought to be clear about which one we are referring to. Okay. Any questions about this? All right, hopefully not too tricky, right? You just got to make sure you are comfortable with the formula, okay? All right. Let's now move on to talk about more mathematical properties. So we basically got heights, and also we got number of nodes. We want to see what will be the lower bound and upper bounds for these two, right? So let's see, okay? So now we are done with slide number 29 and 30 about these two, like a full binary tree and also a complete binary tree. Okay, so now we'll talk about binary tree properties. Okay, let me give you a quick overview very quickly. So when we talk about binary tree properties, we're basically going to talk about the lower bound and upper bound. Okay. The first one we're going to talk about will be what will be lower bound and upper bound on the number of nodes given some heights. Okay, that's the first one. And the second one, we're going to look at what's the lower bound and upper bound for the heights given number of nodes, right? You cannot talk about only one in isolation. You have to given the other one as a context. Given n nodes. All right. And then we also got number 3 and number 4. Okay. And number 3, we're going to talk about the number of external nodes. Okay, and then this will be given the height of the tree. Number 4 will be the number of internal nodes given the height of the tree. All right, so these are the 4 we got to go over. Okay, let's go one by one. Okay, but you know, once you kind of go over, especially the first 2, the other 2 are very simpler to actually see. Okay, let's see. The first one. Let's see the lower bound and upper bound for the number of nodes. Okay, let's take a look at that. And they will correspond to basically the slice starting from 31. I believe there are 4 slices in total, but let's look at all of them at one go. Okay. Let's look at the property. Okay. Given a binary tree, and we know the heights is h. The number of nodes is going to be minimum h plus 1. Maximum 2 to the h plus 1 and then minus 1. So this will be the minimum and that will be the maximum. Okay. So let's use one example to understand about how this property can be satisfied and then we generalize it. Okay. Let's say we got h being equal to 3. Again, what's really h? H here is the maximum depth. Maximum depth, which is about the number of edges to the root, right? It's a very important definition you want to always keep in mind, okay? If h is simply equal to 3, all right? Thinking this way, we are really doing some drawing exercise. If I start with the root, somehow I want to create a tree that's going to eventually give me the maximum depth being 3. At the same time, I want the number of nodes I need to really reach that height to be the minimum. If I have one edge over here and one node, so far the tree is of heights 1. Now I want to create a second link. That second link should really get me closer to the eventual heights of 3. At the same time, I don't want to create too many more nodes. One way to go, if I simply go for second link right here. In that way, I got 3 nodes so far. But am I getting any closer to the height being 3? Not really, right? Because height is still just 1. So that's not the right strategy. So the right strategy to go is to really go for this way. So here I have now created one tree of heights 1. I got another one here. Now I got height 2. I got another one here. I got height 3. So this will be the strategy to go if I can create the minimum number of nodes that will give me height 3. Right? Follow? All right. It's important. Okay. Let's write it down. It also has a name. It's called slanted tree. That means you don't really have any. You don't always have like 2 children at every level for every node. You just keep slanting. Okay. So here, let's say we got the root, and then we got 1, 2, and then 3. Okay, of course, this will be the root. And we say that this is a slanted tree. which means every node at every level, they simply lack either the left child or right child. In this case, they're all lacking the right child. Okay? And then let's now be more precise, more explicit. The number of links we have over here is 3, right? So H is equal to 3. Right? So that's the way to create a minimum case for the number of nodes, given that you got H. All right, so one thing to notice over here, when I have 1, 2, and 3 intermediate links, how many nodes do I have? 3 links, I got 1, 2, 3, and 4. 4 nodes. So the number of links between 4 nodes is exactly 4 minus 1. Right? That's also an important property. Okay? So let's say make it more general. If I have, let's say, the height of the tree being h, and I still want to create a similar slanted tree. Starting from the root, and then I want to go down as far as I can, all the way to when I reach exactly h plus 1. Oh, sorry, exactly h links. So think about here, here, and all the way here. H edges. If I got h edges, how many nodes do I have? Plus 1, right? All right, so h plus 1 nodes. That's exactly how we derive h plus 1. All right? So this will be the minimum case to really reach to the height h. How about maximum? Maximum, you basically want to go the other way around. You want to get to the height as slowly as possible, right? Let's say the height right now is actually 3, right? So what you have is, I start with this, and then I got 1 link over here. But I want to keep the height maybe the same for now, but I just want to create more nodes if possible. Well, of course I can. I just add another child right here. So now here I still have height 1, but I got 2 nodes already. So this is already more nodes than up to here, right? And then if I want to create height 2, I just try to branch out as much as I can. So now I got height 2. You want to get height 3 over here, I, again, try to branch out as much as I can. So this will be the maximum case. So now it's very important for you to compare. If you look at this tree here and this tree here, they look very different, but their height is the same. Now if you look at the bottom level here, for every node here, you got 1, 2, and 3 links back to the root. So height is the same, but they look very different. This will be the minimum case for the number of nodes. This will be the maximum case for the number of nodes. All right? How many do we have over here? So think about, let me put it here. So here, the height is equal to 3. 2 to the 0 plus 2 to the 1 plus all the way to 2 to the 3. Right? 0, 1, 2, and 3. Right? And if you add them up, you're going to get 15. Okay? That's something you can double check. Okay? But how do we generalize it? And by the way, the 15 over here is exactly when you apply the formula over here, it will be 2 to the 3 plus 1 minus 1, where the 3 here is just h, right? You can see the formula, the property here works for this little example, right? Just always good to double check. How do we generalize it, right? To generalize it, let's look at this general tree. Let's say we got this general binary tree here, and then we got h. And then this case over here with the height h, we got level 0, level 1, level 2, all the way to level h. Everything is the maximum, every level. In that way, we're just going to add up 2 to the 0 plus 2 to the 1 plus all the way to 2 to the h. Okay? And this one here will be exactly the one we had earlier. 2 to the h plus 1 minus 1. Right? That's a maximum case, right? I just want to draw the connection for you, right? So I'm going to write it down, but you can review both things at the same time. 2 to the h plus 1 and then minus 1. Okay, so that's why you see this. All right, so that's the first property. Right? So given the heights of the tree, we want to figure out what's the minimum and maximum number of nodes in the tree. Questions? All right. Yeah, think about it. Maybe a little bit overwhelming today. I know we talk about many things, but these are important, right? And look at the second one. A little bit kind of symmetric. So now we say, given the number of nodes, what will be the minimum heights and what will be the maximum heights? All right. We're going to kind of still do that drawing exercise, like a challenge, right, to begin with, to get some intuition. Okay. To start with, let's say we got 7. This means I want to draw overall 7 nodes in total somehow. And then the resulting tree should be as short as possible to be the minimum. What would not be a minimum? If I simply say I got 1 node, 2 nodes, 3 nodes, 4, 5, 6, 6, and 7. This is not really the minimum height. Agree? Because I could have moved this one here to here. I could have moved this one here, maybe to here. In that way, I have reduced the height by 1. So what I just had was not exactly minimum. So the minimum height is going to come out if I try to fill out all the nodes at every level possible. That will give me the minimum heights, right? That's the intuition you want to have, right? Let's double check. So what I have is I start with a node number 1, and then I try to fill it out. So 3 nodes already. I got a height 1. And then I want to get to 4 and 5 and 6 and 7. That's really the minimum I can get to. Right? So here, think about the heights would just be 3 because I got, let's say, 1 and 2. Oh, I beg your pardon. It should be, the height should be 2 because we got 1 and 2, right? 2 links. Okay. Okay, let's double check the property very quickly. I can show you how to prove it. Very, very easy to prove. Okay. What we said over there would be the log of n plus 1 minus 1. As I said earlier, every time we talk about log, if I didn't say explicitly about the base, it's always base 2. Right? Just remember that, right? Okay, let's double check, and I'll show you how to prove a little bit later. Okay, so here, log, we got 7 nodes. 7 plus 1, and then minus 1, right? And then log 8, which should be 3, because 2 to the 3 is 8. And 3 minus 1 will give me 2. So the 2 here matches the 2 over here. All right? All right, let me get to the proving part a little bit later. Okay, let me talk about the maximum heights first, and then we'll go back. Okay, so maximum height will be the other extreme. So if for me to really reach 7 nodes in total, I want to go as much as possible, right? So the maximum case, of course, would be I want to go for 7 nodes, 2 nodes, and 3, and then 4, and then 5. So each time when I add a new node, I actually add the heights by 1, right? That will be the maximum case for the heights. So here I got exactly 1, 2, 3, 4, 5, 6, and 7. All right, I got exactly 7 nodes, which is the example we are working with, right? So think about we got 1, 2, 3, 4, 5, 6, 7. 7 nodes. And then how many links do we have for the bottom node? So from here, 1, 2, 3, 4, 5, 6. Exactly the number of nodes minus 1. Right? 7 minus 1 edges from the deepest node to the root. Okay, and that's why you will see n minus 1. Okay, which will be 7 nodes, n minus 1. Just verify the formula. Okay. How do we generalize this? To generalize it, basically we're saying that the way to really create the maximum heights for n nodes is when you try to make it slanted. Okay. So we simply say we got the root over here and the second level 1 all the way to the bottom level. So what we want to create is all these together will be exactly n nodes. Right? Given n nodes, what will be the corresponding heights? N minus 1. Right? Exactly. Right? So here, you got all the links over here. All the way, you got n minus 1 edges, right? Which is n minus 1 here. Okay. Let's now revisit about the minimum case. If you guys can give me just 2 minutes, and then we can get it done, please. Okay. So this case is basically a full binary tree. We want to see, given the full binary tree, how can we work out the heights accordingly, which will get this particular property. Let's see that very quickly, right? If you look at a full binary tree, like this. Okay, when we talk about full binary tree, this really minimum and maximum will be the same. We got exactly n equals 2 to the h plus 1 minus 1, right? That's what we know from before, right? That one you can double check, okay? Now we're just going to focus on this formula here and try to rearrange the term a bit to get exactly what h should be in this full binary tree. That's all we're going to do. Okay, very quick. So what we do is we're going to start with n equals 2 to the h plus 1 minus 1. Let's start with this. And we are making some assumption without compromising the generality of the property. The assumption is the log n plus 1 is an integer. Okay, let's do that. So first of all, let's now take, move the minus 1. So we got n plus 1 equals 2 to the h plus 1. Right? We simply move the minus 1 to be plus 1. And then we take the log from both sides. So that'll be the log of n plus 1, which will be the log of 2 to the x, will be exactly equal to just x. Right? It's a mathematical property. You can double check that back in your previous math course. So it's going to be the log of 2 to the h plus 1, and which we know this part here is simply h plus 1. All right, almost done. Okay, and then in order to get the h, you can move the plus 1 to the left side, which would be minus 1. In that way, you're going to get h will be the log of n plus 1, and then minus 1. Okay. That's exactly what you will get on the left-hand side. So the way to really figure out the minimum case is look at a full binary tree, which would be the minimum height case, and then try to derive from there. All right, thank you so much. I appreciate it. And then I'll see you guys next Tuesday. Please review, right? It's going to be beneficial for your written test later.